Welcome to everybody who's joining our webinar today. This is the first in a series of webinars from IRDEA, and we're very happy to see such high registration numbers and attendance at today's webinar. So a big welcome to those from obviously our own membership and around Ireland, and also we have a good few people from outside of Ireland as well, which is great to see. As I said, yeah, this is the first in a series of courses and training webinars that we have planned for to kind of improve the knowledge base around district heating in Ireland. With this particular webinar, was the kind of content was decided based on kind of a focused look at the kind of needs of our members based on a survey, identifying the kind of key topics of interest, leveraging and showcasing knowledge and solutions brought to the sector by our members as well as other experts. Just to let everybody know that this webinar is being recorded and will be available online afterwards. Please use the chat Q&A function to post your questions, which will be compiled and fielded then to the speakers at the end. Our first speaker, David Connolly, has to leave the webinar early, so we'll field Q&As for David's webinar straight after his presentation. So if you get the questions in for David first, and all notes will be circulated as well afterwards, so all answers to any questions will also be available offline afterwards. So yes, I suppose without further delay, we'll get started and just introduce our first speaker, which is Dr. David Connolly. He's director and co-founder of IRDEA and also CEO of the Irish Wind Energy Association. And David has been working in the district heating area for a long time and led the Heat Roadmap Europe project in his position as associate professor in the Energy Planning Department at Aalborg University in Denmark. And that project, many of you will be familiar with in the district heating area. It has been one of the most influential EU projects for the district heating sector in Europe, and has influenced policy at both a European level and I suppose at national levels across Europe as well. So David is going to demonstrate how the Irish Heat Atlas can support district heating system design in Irish cities and towns. And this Heat Atlas was commissioned by IRDEA with support from the ESB and was carried out by experts who were involved in the Heat Roadmap Europe project. And that was launched last year. So David will go through now and demonstrate all the capabilities of the Irish Heat Atlas. So David, I'll pass over to yourself.
Thanks very much, Dana. I'll skip the introductions. That's great, Dana. You've done the hard part for me, and I'll skip straight to the good stuff, which is the Heat Atlas. So let's say in a normal circumstances, if we were doing this face to face, I have a short presentation and I'd flip between the presentation and the web version of the Heat Atlas. But considering we're working to the virtual world and just conscious of broadband connections and things like that, what I might do is do a quick run through the presentation first, skip over a few of the details, and then go to the browser and the Heat Atlas online, where I think there's nothing like seeing it work to try and understand what does the Heat Atlas do, how is it useful. And I think there's an enormous amount of information that it provides just around the opportunity for district heating in Ireland. So I'll start, as I said, by running through a few quick slides just to let people know the type of content that I'm covering, and then we'll go to the Heat Atlas online. So just first thing to flag, the Heat Atlas is freely available to anyone. You just go to the IRDEA website, districtenergy.ie. There's a tab there called Heat Atlas, and you can click on it and it'll open up the Heat Atlas in your browser. Please don't do that right now because I'm about to use it to show people on the webinar. So just if you could avoid just going into it till I've finished in the next half an hour or so, that'd be great, because conscious of internet speeds and things like that. This is what it looks like when you open it up. So if you just bear with me for 2 seconds, I'll put on my virtual laser. So you see a map of Ireland. On the right hand side, there's a number of traditional controls that you'd associate with any kind of online map on the top left. And then on the very left-hand side, there's a lot of different layers that you can switch on and off. And that's effectively where the information can be turned on or off on the actual map itself. So you'll see like a few checkboxes and things like that beside some of the headings across the layers. So if you tick those checkboxes, they will come up. again, at normal circumstances, this time I'd probably open it up and start going through it. But again, I'll just go through a few high-level points about it before switching over to the browser version. The first is, just for those who are not aware, one in the Heat Roadmap Europe work, one really vital piece of information we used to always talk about was heat density. So how much heat is there being used within a certain area? And this was very important to define. It was a very good guide at illustrating what actual viability there was for the developing district energy. So let's say a lot of people used to think, well, hot countries don't have district heating and cold countries do have it, but it's actually not at all a relationship like that. So places like Dubrovnik, or sorry, not Dubrovnik, Zagreb in Croatia has a lot of district heating, Milan, Brescia in Italy, as well as very northern countries like Denmark and Sweden. And that's because it's not necessarily to do with the temperature outside, it's to do with the amount of heat you have located in a concentrated area, i.e. urban areas. So the Danish Energy Agency came up with guidance for when the heat density reaches certain thresholds, it becomes more or less viable for district energy or district heating in this case. And so using the heat atlas, one of the really nice pieces of data that the guys extracted for us was how much of Ireland's heat demand is within these heat densities for various viability for district heating. So let's say greater than 300 terajoules per kilometer squared of heat density is very, very high potential for district heating. Basically, there's nowhere left in Denmark or Sweden that has that kind of heat density and isn't converted to district heating. So you can see that about 12% of Ireland's building heat demand is in areas that are extremely high potential for district heating. And again, this is using the heat atlas to extract this information, and I'll show you in the browser how it looks in the map itself. Then there's a heat density range of 120 to 300. There's about 21% of Ireland's heat demand that is in those areas. Again, basically in the likes of Denmark and Sweden, anywhere that has this kind of heat density is already converted to existing district heating infrastructure. I'd say you would struggle to find somewhere in those Nordic countries that has a heat density of those levels and isn't converted to district heating based on technology that's been around for 20 to 30 years already. So that's quite a substantial chunk of Ireland's heat demand, the ballpark around a third of our heat demand that's in areas that most other countries would define as very suitable for existing technology and district heating. Then the third layer is, pending, future technology and district heating, or this is the other key thing that I'll try to show when I get to the browser. If these lower heat densities are right beside these higher heat densities, it can be very viable to expand district heating into these lower heat density areas. So look, I'll explain that a bit further when I open up the heat atlas, but it's just to say that I wouldn't necessarily rule these out as not being viable already today, but they'd certainly be viable with future fourth generation district heating technology and potentially with some incentives to try and expand district heating networks in the future. But as you can see in an Irish context, no shortage of potential to get us started. And this is just to show that the long-term pathway, there's a lot of our heat demand that is in areas. Contrary to belief, many people in Ireland think the heat demand that we have isn't sufficient for district heating, but when you look at the figures and you look at the heat densities we have, it's really, there is a lot of viability. So it's that type of information that having the heat atlas can really put up in lights, and you can extract from the heat atlas itself, that gives you a flavor of what is actually possible for district heating. So I think moving on then from that kind of data at the high level, I just want to discuss briefly some of the layers that are on the left-hand side. And again, I know this is a bit of an unnatural way to present it because I have to kind of go through slides first, but some of the high-level layers that are in the heat atlas that can be very useful. The first one I want to flag is exactly that data set that I just showed you in the previous slide. There's a layer that shows what the heat density is for every location in Ireland on a terajoule per kilometer squared. So that's the first one I'll run through when I open up the browser. But importantly, to try and supplement this, and this is back to the point I was making about sometimes when there's high heat density areas right beside low heat density areas, you can actually economically expand district heating across not just the high areas, but also the low areas, because you're getting the synergy of both. So in the heat atlas, there's not just the heat demand densities areas, there's also this thing called prospective supply districts. And that's where the algorithm in the heat atlas says, okay, well, if I have a high density area right beside a low density area, I can actually soak up that low heat density area as well and expand my let's say, hypothetical district heating system into those areas as well. And that can be very useful to give you a kind of what would a long-term vision for a fully developed district heating network in these urban areas in Ireland potentially look like. I just put in a link in the slides, because hopefully they'll be circulated afterwards, to a presentation that was made last year at the Ardea annual conference, where Morton Dewardale goes and explains this concept of, having high heat density beside low heat density in a lot of detail. So just if that is a bit confusing and people want to get a more elaborate version of that, just have a link there to Morton's presentation. Then another thing that people are often very interested in is, fine, we know that these heat densities are, approximate indicators as to where district heating is feasible, but how much is it going to cost us to build the pipes? And another nice tool that the Heat Atlas has is it has an indicative cost based on Scandinavian costs of what it would take to build the district heating pipes in those areas. It's an annualized cost, so it is a per gigajoule price. So you can almost add this to the number of gigajoules that you could see being delivered, and then the year, probably around 40 years for the pipe infrastructure, if you wanted to get a total investment cost indicator. And again, on that space, there's two layers that I might just briefly touch on. One is similar to the heat density. There's like a map that shows the euro per gigajoule in a nice kind of color palette. But then similar to the prospective supply districts with heat density, there's these total distribution cost curves for uniform areas over a full district that could be very useful when you're doing things like energy planning and so on. So I think the annualized template and color coded system is more useful maybe for a project level guide, but the distribution cost supply curves are more useful for something like an energy planning exercise. Again, just going on with what other layers are in there, there's also an excess heat layer. I should just caveat that the excess heat layer that's in this heat atlas is only for very, very large excess heat sources. So you're looking at things in the region of about 50 megawatts of thermal capacity or more. So there is some of the smaller excess heat, and there's quite a substantial amount of excess heat at the smaller scale that could be absent from this heat atlas. So I wouldn't look at it as an absolute limit on what excess heat Ireland has available, but more an indicative value for some of the large sources. And I know Codima and Donna, and I'll just do a quick reference to that at the end, have done a lot more work on the smaller scale excess heat sources that Ireland could use. So again, I'll just give a flavour of what the layer on excess heat looks like in the heat atlas. There's also layers on geothermal energy and bioenergy in terms of where those resources are located and the scale of those resources in different areas. And I'll touch briefly on that. And then finally, there's some nice tools in the Heat Atlas that I think are two of them that I just wanted to highlight. One is there's a nice ruler tool or distance tool where you can measure the distance from an excess heat source to a potential heat demand. That can be nice as an indicator. Is it 2, 10, or 20 kilometers away? Can be a useful piece of information. And then there's an address bar where you can search a very specific location. You just type in the air code or your address into that address bar, and you can straight away see, is that address or location in an area with a high or medium or low heat density, or is it near an excess heat supply, or so on. So that, again, as I said, that's actually the final thing was just the Codima map I mentioned on excess heat volumes. That's a much more granular look at the excess heat available in Dublin. So if you see this map here, you'll see that in the heat atlas I'm about to present, there's a lot less dots, because the dots that are in the heat atlas are only large scale supplies. But Donna, that's something you can maybe have a quick reference about in the Q&A afterwards. So again, as I said, I'm going to stop the presentation now and just get into the actual heat atlas itself online, which I think is the nicest way to kind of get a feel for what its capability is. So hopefully you can all see my browser now open on your screens. So what I've landed on here, and I had it preloaded, just conscious of the webinar stream and things like that, is the Ardea homepage, so districtenergy.ie, and there's this tab, Heat Atlas. And if you click on that and scroll down, if you just click on the image for the Heat Atlas, it'll open up and look at Ireland overall. So I've zoomed in advance to Dublin, again, just to try and save the internet a little bit. And I'm going to try and avoid scrolling in and scrolling out here. So just to let you know, it's very smooth, just like Google Maps or something like that, to scroll in and out and see how the Heat Atlas works. So what I intend to do now is just maybe walk people through some of the layers that I just mentioned in the presentation, and I'll just take them one by one and give people a feel for what kind of information comes up. So as I said, on the left-hand side here, hopefully if you can see my mouse, just on the left you get all the different layers down listed one by one. So the first one that I'm going to go to, which I think is one of the most interesting, is the heat demand density layer. So hopefully it'll load when I click the layer to turn it on. So what you can see again on the left is different colors for the amount of heat density that's located in that area. So if you just if you look at my slides afterwards, you'll see where I've given I've listed out what this means. So greater than 300 terajoules per kilometer squared, obvious for district heating, should have been converted decades ago. 120 to 300 terajoules per kilometer squared, perfectly viable under existing technology, has been rolled out for 20 to 30 years in other countries. 50 to 120 may be viable if beside a high heat density area, but if not right beside, definitely viable with future developments under fourth generation district heating. And so by just looking at the heat atlas, and as you can imagine, if I had a kind of more confidence in my internet connection right now, what I could do here is zoom in and zoom out, and you'd get a really good feel for specific areas if you wanted to look at them. So you can see, as expected, in the heart of Dublin, there's a very, very high heat density, 300 terajoules per kilometre squared in a lot of the city centre. And not surprisingly, as you leave the city centre, it starts to get smaller and smaller. I think what is surprising when we saw the results of this, and compared to a lot of other EU capitals, is you could almost see the Celtic Tiger development around the edges of the M50, where, you know, right on the spot would be deemed a suburban area. In a lot of other countries, you get a really high heat density in the Sandyford area, again, where there's quite a number of apartment blocks and so on. So it's quite an interesting heat density profile that the city centre is so high. There's almost a low heat density area right on the edge of the city centre, but it actually starts to build up again around the M50 area, where there's been quite a lot of development in Ireland. When you look at that, you know, you can see in Dublin and not a huge potential to use district heating in terms of buildings being located close enough to one another so that the heat density would be viable for pipes to connect them if you were to build it. And as I said, this is more of an indicative value so that you can investigate those areas a bit further. So again, what I'll do now is I'll show that there's a really nice layer that supplements this. So this gives you on every kilometer squared exactly what the heat density is. But the other one I mentioned in my presentation was this thing called prospective supply districts. And that's where what it does is it joins up all the high density areas. And if there's low density areas right beside them, it soaks those up as well. So when I click on this layer, you can see what it shows me is, you know, 20, 30 years down the road, if Dublin was to develop a full citywide district heating system, this is the network and how it would expand across the city as one complete entity. And the reason that that's nice to see is when you click on that prospective area, it gives you a flavor of how big that area is, what the total heat demand is in that area. So this is one number that I might refer back to. I'll just take a note of it. The total heat demand in that prospective supply area in Dublin is around 21 petajoules, or 20,990 terajoules. And then within this prospective area, you can see how much of it is in the absolute no-brainer level of heat density, how much is in the highly feasible layer, how much is in the lower feasibility, but right beside the high density zones so that you could branch into it in time. And again, probably not something that's hugely valuable on a project by project basis in the next 5 or 10 years, but very valuable from given an indicator as to what district heating could achieve in the long run if we were to roll it out at scale. So that's the first two layers that hopefully people now have a flavor of what that kind of information can provide. So the heat density on the per kilometer squared level and the prospective supply districts give you the long-term, what if we went and developed district heating at scale across all the areas where it's actually viable. So I'm going to turn those two off again, just so the map doesn't get too cluttered up. And I'll move on to the next one, which is around the cost. So just then on the cost, there's two of these as well. The first one I'll just show is the kind of like the heat density area. This is a picture of what would be the typical, now I need to stress here, this is just the pipe infrastructure. So this is just the pipes that go down the streets, connecting the heat supply to the heat demand. So it's not the price of the heat supply unit. It's not the price of the heat exchange unit in the building. It's just the pipe network that is going along the streets, because that's a lot of the time what people struggle to kind of get an idea of, is how much would it cost to install these pipes. As I said, it's kind of if I was to give a kind of guidance, anything that's €5 per gigajoule standalone should be very viable for district heating as well. So that's kind of the sister metric to the heat density levels. So if you were to just put a finger in the air and look for a ballpark figure, general rule of thumb would be, if you're €5 per gigajoule investment cost for your pipe work or less, you're in a very good place for district heating to be viable. Now, it depends on a lot of other factors, and I'll give you a flavour of a few of those later in the heat atlas. But again, just to try and provide a proxy. And I think what that shows you is, in a Dublin context, again, there's loads of potential, not just if you look at the heat density levels, but if you look at the corresponding, what we would expect to be district heating network cost for those areas. Similarly to the heat density, this is given it on a per kilometre squared, what would it look like in that specific area. But then, like the prospective supply areas, there's this other layer called district heating distribution supply curve. And the reason that that's quite interesting is, again, it gives you, well, if the whole district heating system was to be developed across the entire area, if you then click on that prospective district heating supply area, it actually builds a custom supply curve cost for that area. So it gives you a flavor of, as you go up 10, 20, 30, 40% coverage of district heating, what is the investment cost in network for that specific area. So as no surprise, if you were to take 5 as a ballpark as to where the threshold is reached, Dublin has a huge amount of its heat demand that could be covered for €5 a gigajoule or less, which shows you a large amount of Dublin's district heat demand could be supplied with district heating in a very economic way, certainly compared to what some other EU countries have done with similar heat demands. So again, this is probably more of an energy planning kind of tool that's more useful, whereas the individual per kilometre squared color template might be more useful for a project by project basis. I should just say at this point, and I probably should have said it at the outset, like, this heat atlas is not built to justify individual project investments. It's almost built as a guiding light as to what's possible in what areas. The stuff that will be presented later in this training course is much more appropriate for that individual project level. But I think this is really valuable as a kind of indicator as to, well, what could it be further down the road, or where could be the ideal spots to go to. But just to add that caveat that we've always said, even in Heat Roadmap Europe, when we develop these heat atlases, because they're trying to look at that full countrywide scale, they are probably only accurate down to around the kilometre squared level. Once you go below that, you do need something more local and more accurate. So look at that. That covers the other the two in relation to the cost supply curves. So the first two were related to heat density, and the second two were related to the cost supply curves. The other ones I'll come to then. The next one is the excess heat. So up on the top, it's the third one down. There's this layer called conventional excess heat activities. And if you turn that on, you'll see in the Dublin area straight away, there's some black dots appear. In the Dublin area, it's predominantly power stations. I suppose just a few caveats again. I think I've mentioned it already earlier. It's only large scale units that this heat atlas includes. So that's 50 megawatts or above. So if you recall back to the CODEMA map that went to lower scale excess heat potentials, it was much more dots on the map than this, and that the reason for that is this has it's large scale units only and above. The other thing I need to caveat is that this data is usually only updated every 5 years. So 2020 is actually the next phase that this is due to be updated, and we'll update the heat atlas when that comes through. But this data is actually based on 2015, because that was the last available data source for what the guys use when they make this heat atlas. So you'll notice, for example, the waste incinerator here in Dublin is missing and will be in the next iteration, I expect. What can be very nice with this heat atlas tool when you have it is you can click on each of the excess heat units. So I'll just move that across. And what it gives you is it gives you an estimated amount of excess heat that could be supplied by that facility. And that's just estimating the number of, again, this is where it's important to just have the caveat for the last time this data was updated was 2015. You know, compared to 2015, these power stations are probably likely to have lower number of operating hours in 2020 than they did then, due to all the wind on the system. So that number may go down, but with all the work that Codema have on all the other excess heat sources, I don't think there's any shortage of excess heat available in Dublin. So at the time that this data source was published, this power station alone had an estimated 7 petajoules of excess heat it could have provided to Dublin, and this other power station had an estimated 5. And then up on the top left, I expect this is the Huntstown power stations, there was another 3 petajoules. So if you just remember back to that number I referred to when I had the prospective supply areas, I think the entire demand in Dublin, that long-term district heating system I referred to, was 20 petajoules. And these 3 units alone in excess heat, so the 7, the 5, that's 12, and the 3, that's 15. So just these 3 excess heat facilities would provide 75% of all the heat that every building in Dublin City would need to get district heating to its home. And right now that's heat that we're simply wasting and is predominantly just going into the River Liffey or into the fresh air. So that's the whole basis for why district heating is an economically thing to do, because instead of losing this very valuable heat for free by paying a small amount of money for it and paying for the district heating pipes, we can get carbon-free heat basically for a very reasonable price and replace a lot of natural gas in the city areas that we currently burn instead of that. And that's the whole basis for why this is justified. And I think that's why it'll be very interesting to see the Codema dots as well, if you look at that report while looking at this heat atlas. I might just mention at this point, because I know I referred to it in my presentation, that measuring device that can be very nice in this heat atlas. So if I turn on the excess heat sources and I also turn on the heat density sources, what can be very nice is I can measure, for example, what's the distance up here in the top left. There's this measurement tool, and then I can just say I want to measure distance, so I click on that, and then I can measure the distance from the excess heat source to Dublin city centre is 3 kilometres. So this one obviously is really short. You know, if I was to think of comparisons that might be useful for people, one of the largest power stations that supplies heat in Copenhagen is about 12 kilometers from the city centre. So again, in terms of comparisons to other jurisdictions, having that scale of excess heat on the doorstep of a city centre is a really kind of appealing possibility for district heating to be developed. If you zoom out of the map and you see other excess heat sources, it can be interesting just to use that tool to see what kind of distances you are from the heat demand centres to the potential excess heat supply centres. So I'll just leave it there. I won't, I'll just so people know what that looks like. I'll turn off the excess heat now, and I'll turn off the heat density area. And the other 2 final layers that I just wanted to show were in relation to renewable energy. So firstly, with the geothermal one, so I'll turn that on first because I think that's a relatively straightforward one. The layer, and I'll try zoom out, and hopefully the internet connection holds through. So you can see on the geothermal layer, what the heat atlas provides is areas which have a suitable geothermal resource that could be tapped into for district heating supply, but it doesn't actually quantify how much of it you use. And the reason for this is that geothermal is not necessarily usually about how much of the resource is there. It's more or less, are you in an area that is suitable for geothermal? And typically then the amount of geothermal you use can depend on things like how much baseload heat demand do you have, because geothermal is usually a 24/7 heat supply. And secondly, what other heat sources have you in the area, because you then have to just compare if geothermal is economically viable compared to what other sources you might have in the area. So what this layer is rather than a quantitative indicator of things, it's more a very useful layer to see, well, could you ever use geothermal in that system if it was developed? And as you can see, the likes of Dublin is right perfectly located within a geothermal zone. And if I chance moving my map you know, you can see the likes of Cork isn't necessarily on top of one, would have to go some distance to connect into what the heat atlas shows is likely to be a suitable area for tapping into a geothermal resource. So less quantifiable, but more of an indicator again as to what you could do in the long run. And then the final one for me then is the biomass layer. So if I turn that on, what this layer does is it gives down to a NUTS 2 level. So the people might be familiar with the NUTS regions. It's the European way of dividing up Europe into different areas. And if you just click on each of the NUTS 2 areas, it gives a breakdown of different types of bioenergy that could be used in district heating as potentially a renewable resource. The reason it's done like that is for district heating, it can be very useful to know your local resource available, because if your district heating plant is in a town or city, you really want to get an idea of what's in the local area. That usually makes it a much more economically viable, especially for smaller scale district heating systems, where the likes of shipping in biomass from global suppliers is a much more difficult thing to do. So the likes of the system in Tralee is using local wood, as far as I know, for their primary heat supply source. And this again can provide some interesting indicative numbers. I should flag that the source of this information is from another project called S2 BioM. So that's where the heat atlas takes its information from in terms of the bioenergy resource available. I think that's it for me, Donna. Like, I know it's a quick whistle-stop tour around the heat atlas, but very happy now to take some Q&A, and maybe I'll leave the browser version open just in case there is some questions on specific things. I might chance zooming in and zooming out depending on how the internet connection holds up.
Great stuff, David. Thanks a million for, yeah, it's a lot of information to try and get in, I suppose, in a short presentation. You know, there's a lot of work and a lot of research went into developing the heat atlas. So, so I suppose if people, as David said, if people do want to go online after the webinar, you'll be able to kind of go dig a bit deeper into the different areas on the heat atlas. So yeah, there's a few questions there, David. As I said, David has another commitment. He has to shoot off too soon, so we'll take David's questions now. So one of the first questions we have in, David, is from Warren, who is asking, what would be the interaction between district heating and the ISEM market?
Yeah, so I suppose I might just turn this off, this share for now, so I can bring it back up if needed. So effectively, it's what is the interaction between electricity production and heat supply? And I think the most obvious place that interacts right now today is a power station. So if you go to Denmark, for example, the way that a power station is dispatched, or let's say selling electricity, can often be very dependent on how the heat demand is doing as well as how the electricity demand is doing. That a huge thing that becomes really vital in the Danish world there is thermal storage. So a lot of the time what power station in Denmark will do is it'll operate predominantly based on what its electricity needs are, and use a thermal storage to keep its heat stored up, so it can then be used at a time where there's less electricity being produced and the thermal storage can be emptied. I think that's the today situation, and that's predominantly what we've seen in the last 10-20 years. I think what we're slowly starting to see now more and more is, as more and more variable renewable electricity comes on the system, especially things like wind power in an Irish context, a lot of district heating systems in Denmark now are starting to install, well, a lot of them have installed electric boilers, and a lot of them are starting to install heat pumps, where, you know, we're starting to experience in ISEM very, very low prices at windy periods. District heating networks in Denmark have responded to that and said, right, that's a really low cost source of heat, so let's install an electric boiler or a heat pump and buy that electricity for a really low price and use it to keep heat. And there's some really great kind of graphical presentations from Danish district heating plants showing how they're, you know, between their CHP plant and their electric boilers and their heat pumps, they're starting to really become very creative with how they supply heat depending on what's happening in the electricity sector.
That's great, David. So another question that's come in from Paulius is around the heat demand density and how are the heat demand densities estimated in the heat atlas?
Yeah, so there's, just so you know, there's a full report on the Heat Roadmap Europe website. Let's say describes this in a lot of detail, just if there is that interest to look into the nuts and bolts in it. But the very high level explanation is it starts off by looking at what's the total heat demand in Ireland's buildings. So it takes that as a national number and it tries to come up with very clever ways to figure out the location of where that heat demand is occurring. Now, I probably wouldn't do it justice in terms of describing the methodology all the way through, but at a high level, what it does is it adds about 5 or 10 layers that indicate to the heat atlas where that heat is likely to be. So for like dwellings, you're using things like it takes a layer where it removes all, let's say, non-inhabited area. So we know that if there's nobody living in that space, then they're not consuming heat in that space. And straight away that gives you a huge reduction in the amount of land where that heat is actually meant to be. Then it starts looking at, let's say, I can't remember the name of the phrase right now, but it's the amount of urban dwellings located within a small area of land, and starts to proportion out, well, if there's a lot of homes built in this small area, then there's likely to be a lot of heat consumed in that area. And it also looks at population distribution. And they tried in Heat Roadmap Europe purposely to do it this way, because after doing these assumptions and trying to benchmark where exactly the heat demand is, they then took countries that have really detailed heat atlases like Denmark and Germany, and they kind of cross-compared, well, Denmark and Germany, we know exactly where the heat demand is. We can be absolutely sure this is it. We have district heating systems where we can measure it. How does this method of trying to distribute the heat demand based on these assumptions compare? And the benefit of that is that for countries like Ireland, where there is no, let's say, localized heat demand data available, that's where they were able to say, well, this is a good indicator. But I would stress that it is only accurate to around just under a kilometre squared. After that, when they compared the assumptions to what the actual demand is, the correlation of actual versus indicative in the heat atlas starts to diverge, and it no longer becomes a very accurate indicator of what's happening. But as I look, that's a high level summary. It's been a few years since I was in the depths of it with Heat Roadmap Europe, but there is a full-blown report if someone wants to get the nuts and bolts of exactly what data and assumptions is behind it.
Yeah, I think it's fair to say that, as you said, it's been double checked, with existing, with actual heat demands, to kind of give a kind of a rely, it's kind of it's been checked and peer reviewed, let's say, as well, and the methodology across Europe, and has been used by other countries as well. There's kind of a follow-on question that I'm not sure if it's aimed at yourself or the reference to the CODIMA map. Again, it's around the heat loads. So the question is from Daniel Barnes: what is the evidence base for the heat loads? And then mentions the CODIMA map for Dublin that was referred to. Are the heat loads from recorded data, or is it an indicative estimate of flow area calculation against benchmarks, for instance? So I suppose David explains where the heat demands for the heat atlas came from, and then for the CODIMA map, it was actually the waste heat sources that David referred to. So that map around the heat sources and the different, as David said, the heat atlas looks at just the very large power stations, whereas in CODIMA, the Dublin Energy Agency, they carried out a analysis of the I suppose other types of heat sources available, not just the large ones, so down to things like data centers and other kind of low temperature sources. And my colleague John O'Shea was in the CODIMA was the author of that report, and I suppose that's available on CODIMA's website, and the methodology is explained there as well. And I suppose we can provide links to these reports and how those estimates were made. But as David said, they're kind of high level estimates, and when you get down to project level, obviously it requires kind of a higher level of analysis.
Yeah, I can send on the Heat Roadmap Europe report as well with the methodology for the heat atlas, Donna, so you can circulate it, or afterwards as well. Yeah,
absolutely, that'd be great. Then we have another question here, David, on if a heat network existed in Dublin using current large excess heat providers, stroke waste energy plant, how would the heat provided be rated on a dwelling's BER versus a gas boiler, i.e. what is the gram CO2 per kilowatt hour from a network?
So I might start by answering what it should be and what it actually is. So in my view, that should be rated as a zero carbon heat dwelling, in the sense that that heat right now is being produced anyway. And if we were using it, there wouldn't be any more heat produced as a result of using it. But what would happen is you would replace some fossil fuel, most likely natural gas or an oil boiler or something like that in the urban area. So let's say Ireland's carbon footprint would be reduced by the equivalent of whatever you're now consuming on fossil fuel. With that pure principle of what's happening in reality, I think the indicator to the homeowner or the person doing the BER rating should be that that's a zero carbon footprint that you're now leaving because you're using something that was being produced and wasted anyway. What actually happens though is you don't get that. There is a carbon footprint associated with it. And Donna, you probably know better than me, but I'm pretty sure it's based on the type of fuel mix that your district heating system has as its supply that's entered into the BER system as your carbon footprint. So it's not effectively taking account of the net gain. It's looking at it as if excess heat is adding a further carbon production, even though it's not.
Yeah, I think that's a good point. I suppose there is additional carbon taken into account, even though it's a waste product that would otherwise is technically carbon free as it's associated with the primary product. And I suppose just as a reference, some of the systems in Dublin that we are planning and are working on at the moment, the CO2, the grams of CO2 per kilowatt hour is a much more favourable option and cheaper option for for dwellings and new developments than other alternatives to meet the same level of CO2 savings, etc. That's required under the new building regulations. So it's a cost-effective option for meeting new building regulations, as well as having a low CO2. But I suppose the actual methodology for that has yet to be decided by the SEAI, but it's something that we're working on with now in terms of trying to establish the primary energy factors for district heating in Ireland and how that should be calculated. Great, I think we have time for just one last question then for David. So from Dara Connolly, he'd like to know what the waste heat from power stations, condenser cooling water, is at relatively low temperatures. Is this useful for district heating?
Yes, I'd say what Ireland has, by being a late starter, is we can use the latest and greatest district heating technology. So supply temperatures to district heating systems now is as low as 50, 60 degrees. I'd say if the power station isn't currently geared to provide heat for a district heating system, I'd say if there was a district heating demand there, it certainly would be. And the reason I'm saying that is if people in Ireland could imagine there's a single electricity market for heat in Copenhagen. So the same way as we think about the electricity market in Ireland, where you have a bunch of suppliers bidding in prices to supply electricity, a clearing price based on who's the cheapest able to do that, that clearing price then setting how much you're going to get paid, and then the different heat suppliers supplying heat to that market based on that price. That's exactly how the heat market works in Copenhagen. So it's such a big market. There's about 7 or 8 different suppliers feeding into it. They bid in a price and it gets cleared. The last year I was in Denmark, and this data might be slightly out of date, the average price of electricity in Denmark was 25 euros a megawatt hour because there's so much wind there. The average price of heat on the Copenhagen district heating system was around 40 to 50 euros a megawatt hour. So if you just digest that for a second, the power stations were earning probably close to twice as much from the per megawatt hour price of heat they were selling than they were for the per megawatt hour of electricity they were selling. Now, if your power station is not able to deliver heat, I can assure you, you'd certainly be making it able to deliver heat in a world where your heat price is 40, 50 euros a megawatt hour and your electricity price is 25. Now in Ireland, we don't have a heat market and our power price is probably closer to 40 to 50 right now. But you know, anyone looking at future power price curves, more renewable electricity we add, the further downward pressure that's going to put on us, similar to what we've seen in Scandinavia. And if there was a heat market there, I think power stations would be more than happy to try and use the excess heat that they're producing to make some extra revenue at a time when operating hours are getting less and less.
Great. So I think that's a I think that's a fairly good answer to that one, David. And I think that's the last of the questions there for yourself. So
great, yeah. So I get to do the high-level picture and leave all the hard work or the detail to the others. So look,
yes,
it's a really interesting tool. I think it's really useful for the big vision stuff, and that's probably what it is. And after that, the real hard work starts, like you're doing, Donna, and the others of trying to build actual projects. So I hope it's useful.
Great stuff, David. Thanks a million, and thanks
for having me.
Time to
See
join
you.
us. So next up, as David said, that was a kind of very high level picture of where district heating is viable, and looking at it from kind of a top down policy making kind of approach as well. So now we're going to zoom down a layer to look at in more detail areas that will be suitable for district heating. And we're delighted to have Matteo Pozzi, who's CEO and partner of Optit, who are one of our founding ERDIA members. And it's great to have a member from Italy on board with the Irish District Energy Association. So Matteo's been working with Optit since 2010. Matteo's a big fan of the digitalization and advanced analytics application to business processes, and trying to build a better and more sustainable world. So he's going to demonstrate now to us how Optit decision support systems help to optimize district heating system development and operations. So Matteo, I'll pass over to you now.
Thank you very much, Donna. I'll share my screen to start with. Please confirm that you see the screen.
Yeah, we can see that.
That's very good. Okay. So I think your introduction was actually very good. We are an Italian company, spin-off from the University of Bologna. Our origins lie in the mathematical and digital world, but we've been working in the energy market since 2010, more or less, since when I started working there. So we've accumulated a great deal of experience in district heating in particular. And you can see that from district heating, we are now expanding our domains of interest and expertise on a multi-energy system. PLANES is a plan for multi-energy systems, which goes very much on the way of strategic planning in a very sector-coupled world. And at the same time, I would like to point out the tension on retrofit, which looks at how energy is used in big plants, industrial plants, and therefore how to retrofit and exploit the opportunities to save carbon in those conditions. As I said, we were not born as energy experts. We're born on, our origins lie in the domain of supporting decisions using mathematics and data analytics. We were lucky to be starting to work with utilities in Italy. I'm speaking of Gruppo ERA and A2A. Two of the main utilities in the north of Italy. Brescia and Milan were mentioned before. I will also use some examples from Ferrara and other places. This means that what I'm going to show you is not just a tool, but actually the condensation of know-how from utilities that have been working in district heating since the late 70s. So a great deal of information that has accumulated in digital tools that I'm going to show you quickly. Just one thing on decisions, because I think that there are two big areas and we are going to concentrate on one of them. There are big strategic decisions on investments, and that's very much the focus of today's meeting. And that goes along with long-term planning. In general, this means how to invest on assets based on the relatively limited knowledge that I've got on the system. Normally, this means concentrating on investment returns, return on investment, and this is very much today's focus. Just for your knowledge, there's also a great deal of short-term decisions that takes place every day once the district heating system is built, which is about how to produce heat, how to mix sources, how to optimize temperatures, and down to intraday decisions, and actually almost a real-time decision at operational terms like pumping, which really goes almost on a real-life, real-time basis. This requires lots of knowledge and information from the field. It's a completely different domain, even though we've been working a lot, especially on the heat dispatching, the so-called unit commitment issue, which we may want to explore in a different session. But let's concentrate on investments and long-term planning. And we do this starting from what a utility company that wants to invest in a district heating system normally has as a challenge. Normally, the point is that there's an area which is more or less well known. The heat atlas that was shown before is very, very good to understand what are the interesting areas. But when we drill down in an area, that normally means that there must be some kind of knowledge of potential heat demand at the building level. There may be deductive or inductive ways of assuming that, but in general, there are proxies that can be used to try and understand what is the amount of energy that buildings may require. This normally is spread across a complex geography. Then there normally are suitable places for heat sources. And the big point is, okay, where should I lay down my pipes? What are the customers that I should try to reach? And how to make sure that this is sustainable. This is an issue which puts together very, very complex economic evaluation, but at the same time, it also has to do with pipes and pipes diameters and pumping setups that allow the heat to travel from the plants to the customers. And this can be quite difficult to manage when the systems tend to become big. Of course, there are situations like in the Netherlands where the political context is very clear. We want to make areas free of gas, so we will invest on district heating and everyone will receive district heating. In that case, there are certain criteria to develop district heating networks, which are normally very good, and they will normally be quite expensive, but that's possible because there are very strong political will to do it that way. The Italian case is very challenging because there's no regulation that really supports district heating. We are working together with the Italian District Heating Association to try to create the awareness at political level to at least create a level playing field with respect to other sources like heat pumps or with other renewable sources that can lead to heat production. But in the right moment, there is a market that must be conquered, and this means that finding the most cost-effective way is an issue. I quite agree, and I was lucky to attend Morten's lectures that David mentioned before, and I think that makes a very, very compelling case to look beyond the low-hanging fruits. But at the same time, understanding how to make a project feasible is a must in many situations. So what was developed in recent years, actually not so recent as we speak, is a tool that maps the decision-making process that companies of this kind make to try to find the best possible combinations of users to link to the network and understand exactly how best to expand the network. What is the measure of a good or an optimal way of expanding the network? Achieving the the best net present value, the maximum net present value, is a typical KPI for the investment decision. And this is difficult because if you think of 100 potential points to be reached, the number of combinations that you can actually mix is a number followed by 33 zeros. So the one single option that maximizes net present value is 1 out of 3, I don't know what, 3 to the 10 to the 33 of possible combinations in the city. And very often the choices of buildings to link to the network is much broader than 100. So that's how our tool was conceived. And of course, since we are speaking of strategic scenarios, it's compulsory for the decision maker to be able to assess multiple scenarios. So we went along on this line, and we developed something that does two things: put together all the economic elements to evaluate the feasibility and the cost of investing in network infrastructure, and at the same time be sure that the key thermoelectric rules that actually govern the fluid dynamics of hot water in the pipes is reflected. And this is a very important thing, because portents are important, diameters are important, pressure drops are important, or really the amount of pumping that you actually need to put in place so that the system holds and is capable of reaching peak demand is very key. So what I'm going to describe shortly is something that has been used to design new networks, brand new networks, but it's also been used for network expansions, meaning taking into account the fluid dynamics and the existence of previous systems, how best to expand that system so that the extra capacity can be reached. In fact, I think it's rather interesting that the first project that we made was on a saturated network. It was the network of Ferrara that you saw in the previous slide, where the plants were actually have already reached the full saturation, meaning that the complete set of existing customers was saturating the network, but it had emerged from consumption data that some customers were not actually using all the contractualized energy. And the idea and the first use of this tool was to understand how best to recontractualize existing customers that were not using all heat in order to create some excess heat without investment on the plant side that could be used to link extra customers. So, in fact, this means that network expansion is not just for the first development, but it actually goes on and on throughout the life cycle of the assets, and very thorough and complicated decisions need to be taken throughout the life cycle. So let's try to understand what are the quantities and the elements that need to be taken into account. Of course, existing all potential pipings and users. To me, a user is the substation, which normally sits at the bottom of the building, but it could be that there are subnets whereby the number of users actually aggregate subnets behind that particular substation. We are speaking normally of increasingly complex plants, supply sides, where there may be a number of different existing plants. For the time being, I mean, this has been tested in various nets, various grids. Normally, the grid operation temperatures is a design value that is pre-managed, even though in some cases that I'm going to touch shortly, that there have been also subnets at lower temperature. One important point is once you are working on scenarios, you need to be able to to manage every single entity in the highest possible detail. And that was actually put in our tool by the means of adopting an existing GIS tool, whereby all the functionalities that normally characterize these systems are actually usable by the user. And then, of course, the capacity to manage the thermal hydraulic model behind the surface, manage all scenarios, and of course manage all the financial and economic parameters. Let's go into some details. When I spoke about scenarios, that means that it must be possible to elaborate different cases where the amount of energy is higher or lower, where the tariffs are higher or lower. Because if we are going to optimize the net present value, we need to understand what the revenues are, and those revenues will be based on the actual cost, the actual tariffs that are imposed to users. Therefore, one of the starting points is to create what we call an instance or a network actually allows us to run through a very, very complex tree of scenarios. I remember that when we first deployed in HOA in Milan our solution, during the user acceptance test, we went through 23 different cases in one morning. And I remember that the users were telling that possibly doing the same job in normal operations would have taken weeks. I've also added one other tab that the system has, because that helps me to go through what normal information that needs to be available is. So when we speak about the network, that's normally a matter of nodes and branches, so the pipes and the points where branches meet. Of course, this is if that is available in existing tools. There are shapes files already, even though the system allows actually to draw the network directly on the map. Of course, plants need to be located with our characteristics. Users, both existing and potential, must be put there. It is also normally quite handy to be able to both load background maps that allow you to navigate the geography of the area with some ease, and sometimes barriers, because some calculations, some elaborations are made automatically. And it must be very clear when you link a customer to the closest pipe that, for instance, no river should be crossed, or no railway line or tram line should be crossed. Of course, it is always possible to cross these lines, but imposing it with manually, so that you take into account the extra costs of investment to do it. As I said, it's very, very important that all elements can be characterized in the finest details. Of course, there are standard elements that can be imposed across the database, but then the user is capable of putting, I should say, in time, this has grown up to cover really a big breadth of details, because the actual way to come to a feasible and usable scenario must take into account all the subtleties and the details that a fine design actually requires. It is also true that when you work on scenarios, some massive operations sometimes are useful, and normally just selecting a number of pipes or points, it normally is quite handy to change the tariff type or status. By status we mean if it's a potential customer or a contracted customers, or a must be contracted customers, or stuff like this, or lock their meters for potential pipes. So lots of information on the technical and physical side, but also big decision to be taken in the economic side of things, because The revenue side must take into account tariff configuration, and one of the big uses of the business planning of design and investment must actually take into account that the money that you will make out of the district heating will depend on the tariffs, on the discounts, on the contributions that the customer will actually have to may have in the investments to link to the network and stuff like that. We've seen lots of very interesting scenario analysis on different tariffing conditions. Of course, since we're going to be looking at investments, we need to be able to put down the costs that can be fixed, base meter, extra costs, etc., substation contribution costs, etc., for all different pipe types, plus all the elements that allow to make the financial analysis evaluation, which is amortization times, both for connection and substations, tax rates, etc. And maybe also something that takes into account the uncertainty of being able to actually connect users in time. This has taken the form of an acquisition curve, thanks to the contribution from our colleagues from A2A, which actually have used their experience. Down there, the numbers here are not real, of course, but based on their experience, they know that if they go in a certain area, maybe in the first year you will actually be able to reach a certain amount of customers, and then in the second year a certain other amount, and so throughout the years, and maybe you will never be able to actually bring on board every single possible customer in the area, and that actually needs to be taken into account, because assuming that everyone will join the district heating, sometimes it's just not feasible in a free market like the Italian one. So, what then happens when optimization is run? What you see there as red lines are the potential pipes, which means where I may expand my network. The red points are the potential users. You understand that there are, behind each of these users, there's a potential heat and therefore amount of revenue that could be generated. And out of all possible combinations, the optimization tool will select the subset of pipes and customers that maximize the net present value. This means that the very high level of complexity is assumed behind the system. And the good point is that everything is automatically validated with the thermal hydraulic model, meaning that the diameters of the pipes are the minimum viable diameters to be able actually to serve all the yellow subset of customers that you see here. So there is an embedded hydraulic feasibility scenario, sorry, because I'm covered, my image is partly covered by the speakers, okay. The nice thing is that all pipings diameters are actually optimized to run that particular scenario. Now, is this what will actually be built? In general, the answer is no. Because there's lots of intelligence that can be put there, which may require to close a loop for safety reasons. There may be customers that we already know that will not be willing to link to the network, and we can exclude them. There are, I may want to take into account that there are further development areas beyond this point, and I may just take that into account, creating a sort of virtual customer that allows me to account for future developments. So playing with scenarios is really what the big feature of such a tool. This is actually what any planner would like to do, because these systems are normally so complicated and so cumbersome to actually track both in economic and physical terms that normally common sense and good rule of thumb is normally applied. And having a tool that allows you to see what happens if costs increase by X amount, if I put a discount to attract more customers, etc., is actually very, very, very important. The actual outcome of such analysis is, on the one side, a full full investment analysis. And investment analysis means I need to know a cash flow trend. I may be able to impose the fact that certain investments are only made in certain years. So I can actually play with this quite a lot. And the actual value that the solution has will normally be the signal of the feasibility and the economic sustainability of my scenario. At the same time, I can use all the thermal hydraulic model that lies behind the surface to be able to actually depict all the elements in terms of, for instance, pressure. So in a graph like this, I can see how pressure goes along the network and maybe understand whether there are critical areas or elements whereby I should, for instance, require the design of extra pumping stations throughout the line. Since being able to navigate the solution is so important, we've actually added a business intelligence tool that sits on top of the system that actually is being currently used with great success to compare scenarios. So what you actually do here, you have your big scenario tree. There will possibly be 2 or 3 hypotheses that you're willing to analyze better and to compare. Just by selecting these hypotheses, you can then get a very intuitive way of understanding where the critical points are, all the key indicators, both at technical and economic level, both input and output parameters. And very nicely, the capacity to move throughout the map, zoom in and zoom out, and see how different scenarios compare. This is actually proving very, very useful to understand and reach the point where you actually can be convinced that there is a situation that it's worth investing to bring it to the construction phase. And this is exactly what happened in Milan. Actually, the challenge that Milan asked us to support them with was this interconnection between 2 previously unconnected grids. They basically built 6 kilometers of pipings that were running through fairly densely populated area of Milan. They knew that they had to allocate something in the region of 100 megawatts of power. And the idea, the question was, okay, but since everything is so attractive, where really should I allocate this power in order to increase my return on investment? So the 2 lake hours was actually used to study all different areas that you can see painted here, and understand where best to allocate things. And in the time frame of a couple of years, all power was actually allocated with great satisfaction on the sustainability of the whole thing. I think the most interesting lesson learned in that occasion was that by putting in the same place both the economic and technical decision drivers, we found that the system that had been conceived and designed for engineers was actually used by the marketing and commercial department. because in the end, those who knew where the customers were the most interested in creating scenarios. But the good thing was that the tool allowed technically feasible solutions to be brought to the engineering department, which actually speeded up also very much the final design of the networks. I don't want to bore you with other references, but I think it's interesting to see how putting together technical and economic values was used to support the District Energy Cities initiative of the UN environment to study the Belgrade network in Serbia. That was a massive project, very important, with lots of huge impacts. And that really allowed to study the design of new interconnections in order to make the most of a very large waste heat source that was going to be connected and will likely be connected in this area to provide heat to the old city of Belgrade. More recently, we applied it in smaller places in Germany and Sanchilinkai, both to study expansion scenarios, but also to analyze refurbishment strategies or study the opportunities to allocate existing grids to low temperature grids and optimize the relationship between high temperature and low temperature grids. I think I've run slightly quicker than expected. I wanted to, at the beginning, I think I wanted to run a demo, but maybe the time was not sufficient to go through all the details. So where I am right now is, of course, the tool is available. This know-how can be accessed. The way to actually support any analysis on district heating expansion or development scenario is available, and we will be very happy. And that was actually the first reason for us to join the EODEA and be one of the founding partners together with all the others that created it a few years ago. So in case there was any interest in understanding and leveraging the tool, these are the phases that you can think of. There's a time for data collection. Of course, this means that the actual parameters for actual costs that you think you're going to be incurring with, and the positioning of customers, the geography of systems of your plant, everything needs to be in some way available. But that's anyway something that you need to do, whatever system you need to design. Once that is available, there is normally an early setup an early analysis. That means that once all the information is put in the tool, there is normally a preliminary analysis and validation, and normally based on that, a fairly large and sometimes very large number of scenarios can be analyzed and worked around with in order to explore all the possibilities of your system. Let me just reinforce the fact that the methodology that has been structured in the digital tool is really what companies have been doing in the last, I mean, since inception of district heating. The difference that the digitalization allows us to is to be able to be guided throughout this, both having very strong simulation features, and I think that this is something that can also be reached by employing different other tools. But maybe the nice and the beauty of some novel approaches is to put together simulation with optimization in order to be guided through and to the maximization of objective function, which normally is, in this case, the actual economic sustainability of the investment. And you also say that the previous project in Belgrade allowed us to benchmark the system with respect to existing commercial tools like Termis or SCADA data. And it is quite nice that we actually were totally consistent with those kind of elements that unfortunately are not suitable for design purposes, because very often simulation tools like one that I mentioned is very good for operational simulations, but are very much based on data coming from SCADA and are more difficult to use in design exercises like the one that we are interested in this session. Okay, I've run through the conclusions. I think that I mean, I'll be available for Q&A when Donna thinks that these are. I mean, I can either do it now or later. I will let Donna to run this. I just want to restate the fact that tackling network design exercise is a very complex matter. The details are important. So the drill down from an apparently very smooth and easy decision that normally appears from a high level perspective actually requires a lot of analysis when the actual feasibility phase is tackled. And I think that there are nowadays very interesting and important tools that can be used to support complex decisions and sometimes also to reinforce already taken manual patterns that were studied in already very well developed scenarios. I remember in many situations, I remember in some areas of Turing, we were actually asked to benchmark the solution that had already been agreed to be developed in order to see how optimal they were. And it was actually quite interesting to see how with the same input data, an optimized scenario would actually lead to a solution with about €1 million difference in complex net present value, which of course means that the job was very well done, but there could have been options to actually maximize and optimize further the financial and economic sustainability. We will be very willing and happy to answer to your questions and eventually to go deeper in the tool, maybe next time with a demo or just go on a project supporting with an advisory or software as a service agreement in case there was anyone who was interested. And I think I would stop here and just let me know whether you prefer me to answer questions now or later.
Thanks a million for that, Matteo. Very detailed presentation there of the software tool and all of its different capabilities, which, as you say, are very important. And it was really interesting to hear how it was used by not just the engineering, not just as an engineering tool, but also from a commercial and marketing perspective. That it's also very important for those teams to have access to a tool like this.
Yeah, let me just say one thing, because your comment allows me to reinforce a point that I think is very crucial when tackling a network design phase. There is normally very much attention on the technical side making sure that the pipes are designed correctly and the diameters are correct, blah, blah, blah. But very much of the success, especially in difficult markets like Italy, this is crucial, actually lies in the business model. So the cost for the end user of the district heating makes a hell of a difference, and understanding how to make it feasible for the user to adopt the district heating as a feasible option, but also to make it sustainable for the company is the real challenge. Funnily speaking, the business model and the commercial criterion are at least equally as important as the technical and engineering details. And that's really why we were brought by our customers to think of something that puts together both decision drivers in one place. So maybe this is really it could be the most important message I could leave to our audience, that district heating is not just a technical element, but it very much has to do with commercial and business modeling
absolutely
expertise.
Yeah. We definitely agree I'd say from an Irish perspective anyway, that yes, it's not just all about what's technically feasible. That's where you might start out, but obviously the business model and the commercial details are where it really counts. We have one question in, Matteo, that we might take now, just before before we jump back into the next presentation. So we have one question from Gio, and it's, what percentage of heat energy required is produced from solar energy? This might be in reference to one of the earlier projects you mentioned in maybe Zagreb or somewhere.
Okay. To be honest, it depends. I mean, our tool will look at the supply side as points that are capable of providing a certain supply with certain characteristics. A tool like this normally doesn't look in the supply side as a decision, because that follows completely different patterns, and of course those are very important decisions that need to be taken together and side by side with the network. So we've seen and we've analyzed the cases in our previous projects. Actually, projects like the one that I wanted to close the presentation with, which is UpgradeEH, which is about retrofitting existing assets. But I think it's a very interesting source of material for everyone who's interested in district heating. And maybe I like to close this presentation by pointing you to the handbook and the best practices that I think can really shed a lot of insight. There are in the material of this website, there are cases where solar district heating was studied as an option. I think it was in Lithuania and in Bosnia and Herzegovina, and these are feasible options. But how that mixes together with the other sources really is a matter of fine balances that depend a lot on the specific features of the place, of the cost or incentives that are present at local level. So it's impossible to say in general. I would say that solar energy is a very interesting option in many places. You can see there are some Mediterranean countries here involved, which of course is good, even though, as we all know, the largest solar plants are in Denmark, which makes us Italians laugh quite a lot, but that's how it goes. I think it's a cultural matter, to be completely honest. So I'm afraid I cannot answer to that question, just because the energy mix and the plants that are most suitable for the district heating supply are sort of, I mean, it's a decision that will be taken aside the network level, but I mean, it's not a tool like this that provides answers in that respect.
It's a good indicator, as you say, Matteo, that some of the largest solar thermal plants in Europe are in Denmark. As you say, the Mediterranean countries probably have a little bit of catching up to do there, and it is a very it is a very feasible solution, particularly for rural district heating solutions where there's a lot of space available. And obviously, you know, once you have the system installed, you don't have ongoing fuel costs or, you know, or that kind of thing into the solar supply. So it's a very cheap way of providing heat, particularly in summer, and then we're coupled with seasonal storage and that kind of thing can increase its supply all throughout the year. So we might spend all of the questions at the moment. If you do have questions for Matteo, we might have time to take them at the end if people do have still some questions left. But I think we'll move on now to our last presentation, last but not least, to another IRDIA member, LogStore, and Mr. Paul Atkinson, who is the technical sales engineer for LogStore UK and Ireland. And Paul has more than 30 years of design and engineering experience in the construction industry, and his role includes providing advice and support to consultants, energy suppliers and installers across all aspects of district heating, so including the design, installation, products and project execution. So he's a lot of experience there and a large range of skills to share with us. And Paul will present the key aspects of piping system design for quality, reliability and low life cycle costs. So this will go right down to the pipes now, to that level of detail. And Paul, I will pass over to you to take over now.
That's better. Thanks. Thank you, Donna.
No problem.
Bear with me 1 minute. Okay. Yeah, thank you, everybody. Obviously, we're in a bit low on time, so I've popped a little bit out as we've been speaking, so we can all get away at 4 o'clock, or we can get into the questions at 4. So I'm just going to talk very briefly about design of the district heating pipe system. It's a fairly large subject. However, I'm going to try and condense it down into 30 minutes. So it is just the bare bones. But yeah, so basically we've got the pipe system, which I'm not going to go into the dimensioning, the pressure drops, etc. But then I'll go into the types of casing joints, spatial and static design, heat losses, and I was going to talk about total cost of ownership, which Matteo was discussing really earlier on, so I'll drop that out of the presentation. So who are LogStore? We're basically a Danish manufacturer of insulated pipe systems. We've been developing products since the 1960s and supply to markets all over the world, including obviously Ireland. In a nutshell, we provide solutions to transporting fluids, minimising energy losses. So I'm here specifically to talk about district heating, but our UK and Ireland office also covers district cooling and industry. So industry is basically anything from minus 250 degrees up to plus 250. So things like things like steam, high temperature, etc. And then we've also got a separate division which supplies oil and gas, which obviously won't cover here. So the pipe system. The pipe system is the most critical part of the network in terms of carrying the energy or the heat from the energy centre to the point of distribution. So very quickly running through the pipe makeup, we've got typically 3 and sometimes 4 different layers. First of all, you've got the actual meter pipe itself. They come in various different options, so steel, copper, Aluflex or Alupex, and PEX, so plastic. And then we have insulation. So typically in a district heating pipe, we'd have polyurethane, which is PUR, which goes up to a maximum of 120 degrees or a peak of 140, up to 300 hours a year. And then if you want to get into district heating but higher temperatures, or you are going to the steam end of the market, we do PIR foam, which does up to 170. We have the diffusion barrier, which is basically an aluminium foil which prevents all the gases diffusing, but I'll talk about that in more detail at a later presentation. And then we have the casing, which is a protective casing, which also assists with the expansion mitigation by transferring the loads from the steel all the way out to the casing into the sand, mitigates that. And that's basically high density polyethylene. And then we have the adhesion between the layers. So the steel surface is shot blasted, and then there's corona treatment of the PE, which makes all of those layers act as one. Like I say earlier, it really helps mitigate the expansion over and above what you would have with an unbonded system. And then we can get them in a pair of single pipes for flow and return, or if you want, you can have them all in one single PE casing, which is your twin pipe. The next consideration in terms of design is what series or what insulation thickness do you want. So again, I'll talk about this in some more detail, but the insulation is basically is really looking at how much that heat you will lose over time, and that's the key element really when we're looking at system design, and it's balancing the cost of the actual capex against the operation and maintenance costs, obviously the fuel source that you're going to use over time. But you'll be looking then at your pipe. Do you want it in copper or steel? What are the lengths? And then you've got different operating and temperature considerations. So for example, if you wanted to have an 85-degree system, fairly lowish temperature, then you could use the Aluflex or the PEX, but you must then bear in mind what's your operating pressure. So for example, the PEX would go up to 6 bar, Aluflex up to 10 bar. If you're outside of those, you've got to go with steel basically. You haven't got any other option. So we're a one-stop shop for all components. So we've got pipes, reducers, bends, and then various types of branches, 45 degrees, parallel straight Ds, etc. And then depending on the media pipe, you've got different types of joints. So obviously with steel, there is currently only one way of joining those, which is the traditional welding, and that type of welding will be determined by one, the consultant specification, but predominantly by the welding technique that's appropriate to the wall thickness of the steel. And if you're in the realms of the plastic PEX and Aluflex pipes, then we're looking at bespoke fittings which have to be fitted, with the appropriate tool designed specifically for the job. That's with a pair of pliers, as I'm sure has happened occasionally on other projects. I'll just go very quickly into a little video which is off our website. We've got several different teaser videos which take about 2 minutes, and then we've got more detailed videos which can be used for refresher training, etc. I'm just going to go through a band joint system, which is predominantly one of the ones that's used in the UK and in Ireland. So basically this is these are the wires that are pulled across to continue the leak detection system. We put in a depth guard. Those then have spacers to keep that depth guard from pushing into the pipe and keep that nice and constant and the whole thing rigid. Those are cut off once they're at the correct length, and then that's taped with some foam to protect the casing. Cleaning and abrading is absolutely essential when it comes to band joint fitting. So that's the casing going on, being tightened up, the clamps being positioned. This is the old style of branch, which will be phased out, and we're going to a much simpler one currently. So that's the Weldmaster being all plugged in. We've got the PDA there. You'll scan that with the barcode, which then puts all the correct temperatures and pressures into the Weldmaster. Turn on the Weldmaster, it'll go through its sequence. That will generate a yes, no, it's gone okay or it's not okay. And that will also then provide you documentation up into our server. Now we're doing a simple leak test, and then finally foaming up of the casing. Knocking the pressure release toggles off, and then with the open weld mirror, fitting the weld plugs. And that's pretty much it. So that was the insulation, that was a band joint. The choice of the type of casing is very critical really. We've got two different types, which is a shrink joint, which has mastic in the end. Once that's heated up, the casing wants to return back to its normal size. So these have been basically expanded out, and then when you put some pressure on it, in the form of some heat, it shrinks that back down. Before you obviously do that, there's a mastic seal that goes around. If you want to go with the welded joint, which is, I would say, probably UK and Ireland is about 90–95% the welded joints. That, as I've shown you there on the video, but there's limitations with the shrink joint. They can't be used in contaminated ground where they can degrade the mastic, and if the water table is greater than ½ metre, it gets the water pressure can build up and be too great for the mastic. The benefits as well of the welded joint over the shrink is that you've got fully automated process there. It doesn't rely as heavily on the operative, and also you've got resilient QA documentation that goes with it. We've got something like 800,000 logs stored on our server now, and there's the graphs. So that's the automated joint system, as we just said on the band joint, using that 2D barcode, which gives information about that. And then there's basically for every single joint that's done with that Weldmaster, you get one of these curves, which gives the pressure and the temperature curves going up, and the voltage and current in that joint. And then it shows you the cooling off period as well, to make sure it's cooled down properly. Those are saved on our database, along with a GPS location of where that was actually taken, so you can have future-proofed text going back at some point in the future if you need to. All joints are tested in the sandbox test, so they have 100 movements in accordance with the EN standard EN 489, which gives obviously a long lifetime and quality installation, quality products. We're constantly evolving the products, little tweaks happening all the time, just to make things as best as they possibly can, learning as we go. So once you've decided on your pipe series of insulation, your media pipe, and your joint, we'd then start looking at the spatial and the static design. So you need to start looking at the routes. So first off, spatially, where are you going to go from the energy centre, where are you connecting to, and how is it getting there? So that will naturally introduce Z-bends or elbows where they need to go around corners, for example, or if you need to go around a manhole, as another example, that would naturally put in a U-loop. These can then be used to mitigate your expansion. So looking at the design, really, you've got your straight runs. What is the acceptable stress limit? Are you going to use a reduced one for a really increased service life? You might want to be going for 70 years or more. Or are you going to stick with standard codes? What directional changes? How are you going to make those? Are you going to make them with curved pipes? Are you going to have L's, Z's or U's? And then at each of those, you need to analyse the movement and look at the angles of those bends and how you're going to get around them and check them statically. And then you've got your branches, where you're going to place your branches to make sure that they're in the area that isn't moving, so in the lock zone, preferably. And are they going to be 45s or 90s? What's the length of the branch going to be? What's the length of the parallel section, etc. And then are there any reductions? And those reductions, if they're single, they probably can go next to each other. But if you've got double reductions, you're going to have minimum separations to prevent pressure build up and losses, etc. So static in itself is probably a half a day presentation, but just very quickly, those are the key elements when you're looking at the static design. We have the online calculator, which helps yourselves, or if you put it into Logstore, to do the static design for you. We've got the tool online on our website, and use lots of different parts to that, but specifically talking about the expansion zone, we're looking here at foam pads for a Z bend. You can look at U's, you can look at Z's, you can look at house entry pipes, etc. So it's basically looking here where we get in the maximum stress, and what do we need to do to mitigate that. And as a consequence, it gives you this output here, which is basically the number of foam pads required. Interesting point to note is that foam pads should be inside and outside of the bend, not just on the outside. And there you go, a job there with all the foam pads installed. So heat losses. There's basically three different methods of production of pipework. So we've got traditional types of sandwich construction. Then we've got an axial conti, which is extruded basically through a continuous line, where the pipe and the casing and the foam are all integrated in various stages over a production line of about 100 meters long. And then on larger diameters over 315, we have the spiral conti, which is where it's effectively sprayed onto the pipe as it goes through the machinery. And then if you look at the corresponding lambda values, you can see that the actual conti there is giving you the greatest reduction in heat loss, followed by the conti, and then the traditional. The big effect really of that diffusion barrier is to prevent aging. So what we have in our foam, it's not the foam that's actually providing the insulation. All the foam is doing is simply a carrier to put some closed cells in there, and those closed cells have gases in them. So we've got some really good gases in there, which are really high insulating gases. So cyclopentane, we've got 0.012 lambda value, and we've got CO2, which is 0.017. So it's really really good at insulating. Over time, though, in a normal traditional casing, that will diffuse out, and then they'll be replaced by nitrogen and oxygen, which are poor insulating gases. So if you look here at the aging curve, so traditional series 1 that I've given here, if you look at the smaller sizes, that's a massive difference in terms of putting how those gases diffuse, and over time you'll see how the particularly look at the DN25, DN40, DN80, you're losing a huge amount of those high insulating gases over time. Yes, a lot less so as you get to the higher dimensions, such as 600 diameter. So to overcome this, we have this diffusion barrier, which is an aluminium foil, which is in pipes up to 315 outer casing. And that is effectively installed at the manufacturing stage, and that keeps all of those good gases in. It can't escape, and so that lambda value that you have on day one when that pipe is produced is retained over the next 30, 40, 50 years. And so the heat loss basically just stays exactly as it was. So if you look here, you can see typical DN80 Series 2 traditional compared to a Series 2 actual continuous diffusion barrier. We're getting 20% year on year energy saving, which when you look at it over the lifetime, maybe 30, 40, 50 years, that can provide a massive saving. Obviously, there are capex the elements to decide on that. But if you're an energy provider, you're selling that energy, then it really is worth looking at that diffusion barrier or going up to higher series. So, for example, if you've got just simply a traditional Series 1 pipe compared to a traditional Series 2 pipe, we're looking, over a traditional Series 1 to a diffusion barrier Series 1, with probably a 10% or so increase in capex, you've got 23% every year saving on energy, and that makes a huge difference when you model the project. So in summary, I would say that we basically have the media pipe. When you're going through the different stages of designing the pipework, you start off with your media pipe, you look at the material you're going to use, looking at the pressures and temperatures. So are you going to go with steel? Can you go down to where your pressures and temperatures allow you to use PEX or AluFex? That will govern to a large extent the type of pipe. And then what are you looking at then in terms of the insulation series, and do you want a diffusion barrier in there? So it's a combination really of looking at your capex and then comparing that to your operating costs over the lifetime of the project and see where that balance is. Look at the type of casing joint. So are you in contaminated ground? Have you got high water table? Do you want the extra assurance of quality and those QA records that go with the fusion welded joints in the form of EW or band joints? Once you've decided that, so you've got your basic parameters then in terms of your actual pipe type, and then once you've got those, you can start looking at your spatial and your static design. So, for example, your designer will be looking at existing services, existing routes, levels, etc., and that will largely dictate that. And then you can start to overlay where your branches are, where your maximum runs need to be. Are they too long? Do I need to introduce compensation loops? Have I got any naturally that we could put in? And basically that comes up then with the layout. And then we go into total cost of ownership, which I haven't included today, but we have a tool that basically looks at the different types of series of pipes. And if you go onto our online calculator, you can create yourself models, and that will there show you for a given scenario of different type or blend of pipes, you can look at the energy losses or heat losses over the course of the project, compare that to your capex, and then make a balanced judgment on whether you want to put some slightly more investment up front for a longer term gain, or are you really up against it in terms of your capex, or have you got other drivers that are involved that maybe you just want to go with a basic series one without diffusion barrier, for example. And then I haven't again included this today because it's a whole presentation in itself, but leak detection. So with steel carrier pipes, you can't do it with plastic, but leak detection, if you put an active leak detection system in there, that is going to give you your 30, 40, 50 years of operating, because you'll be able to see if there's any problems with that system as they happen, and you can react to it rather than that spreading, you not knowing about it, and your system degrading over time, your lambda values going out of the window, your heat losses going up exponentially. So that's a separate subject. And that was it. Thank you. Hopefully I've caught up a little bit of time for you there, Donna.
That's great, Paul. I think you've made up a bit of time there, but we still have scheduled until 4:30. So I think we've a bit of time there for questions. So I suppose we'll open the floor then to any participants that have questions for either Paul or Matteo. Paul, I've used your online tool myself, the Logstore online tool, found it very useful. So I'd recommend people and we can share the link, Paul, I presume, afterwards as well to participants.
Yeah, that'd be good. Yeah. Please, it's just there it is, basically, just to quickly show you it. So yes. You've got your energy loss. If you want to produce your if you want to, what was I going to say? So you've got your energy loss calculator, or you can look at actually creating some static designs here. So you've got your friction lens, install lens, foam pads design for a 90, foam pad for a U, etc., etc. So it's a really handy tool for helping you design your systems. Yeah,
we found it very useful now. For some of our kind of initial feasibility, to be able to kind of plug the numbers in there and give us some idea of the types of pipe sizes and insulation levels is really really useful. So I'm just checking again for questions here for you, Paul. There are 2 questions, but I think they're more aimed at probably the Irish side of the water. It's probably aimed more at myself and David more than. So the questions are from Fergus Sharkey, who's asking, are there structural or cultural issues in Ireland that prohibit municipal heating utilities from forming? And is it more viable to start smaller community district schemes or schemes with a smaller number of users bought in from the outset rather than larger city-wide schemes? I don't know, Paul, if you have any thoughts on that, and maybe the second part in terms of from your experience, do you think maybe smaller schemes are easier to start out with, or?
Smaller community district schemes. When you talk about targeting smaller community district schemes, I think Morton does a very good presentation. I think Matteo mentioned it earlier. Is that potentially there are, in any project, there are some nice low-hanging fruit, and you can look, if you've got a pot of money, people tend to use that where it's actually going to get them the greatest return, which is natural. But you need to look at these really as a whole, in that if you can bring in other smaller developments, as well as just looking at your low-hanging fruit. So it may be that you're running, you may be running past these smaller community schemes, which you've got the potential then to connect them into the large scheme. But if you have them, then you could design them as a standalone community scheme with its own energy centre, with the potential, as the particularly you're developing these schemes as you go in, is to potentially switch off that energy centre in the future and connect into a bigger, more city-wide scheme. So
it's building up the nodes, isn't it? Yeah, it's generally how they kind of spread, is starting with smaller individual schemes and then connecting them together. It seems to work in a lot of jurisdictions.
Yes, definitely.
And Fergus, then just from an Irish, I suppose, point of view, then in terms of the structural or cultural issues in Ireland that prohibits municipal heating utilities from forming. I think prohibit is probably a strong word, it wouldn't be the right word. I think it's more, it just makes, I suppose, the way the level of autonomy that the local authorities have to act in the energy area, and their experience with being energy utilities is, I suppose, an inherent disadvantage, for local authorities, particularly in Ireland and possibly in the UK as well, where we don't have the same kind of experience as they would in other municipality areas and other kind of regions across Europe, where they would have, municipal electricity systems, and they would control the kind of, in a lot of cases, they'd be the DSO for the electricity grid or the gas grid in those areas as well. So it's a natural add-on, I suppose, for municipalities in some other countries. So I suppose in terms of culturally, then yes, we don't have the same, the same experience, and as well, we're probably not as socially, I'm going to say, socially minded, let's say, as the Scandinavians in some ways. So maybe cooperatives aren't as natural to don't come as natural to us as the Danish or the other Scandinavians. But I think that is starting to change. We are seeing more cooperatives and more small community groups setting up and coming together under the whole climate action area in general. So I think it's definitely an area that I think has great potential to grow in Ireland. And the second question on, is it more viable to target smaller communities and district heating schemes? I suppose, again, it depends on how you define more viable. It mightn't be as viable because, the large district heating demands, and I suppose a lot of the times the large waste heat demands, so your kind of cheaper sources of heat, are located in urban areas, and they're generally the areas that you would target first. But I would agree that the less stakeholders you have involved, the easier it is to get a scheme off the ground. So if you do have a small community, a rural community, or a smaller scheme who, do have a genuine interest and kind of want to come together, it's likely that that's going to be a lot more, let's say, easy, less barriers to come up against when you have a group of people who are already engaged and want to come together to develop a scheme, rather than trying to start it, I suppose, at a big challenge like a city scheme. It gets a little bit more complicated, and kind of around the commercial aspects and relationships there. But I think we'll open up the floor. There's some other questions coming in.
Sorry, Donna.
Oh, yeah.
This is John here. Sorry, I'm going to be selfish and jump in with a couple of questions for Paul. Sorry. Paul, I was just wondering, from your own experience in the UK, particularly, what sort of common installation problems you've come across, in new markets like that. Like I've heard stories of, sandpaper being used for cleaning casings, and that causing issues with kind of fusion welding of the casings and stuff like that. Yeah. And then second question then, just in terms of product development for Logstore, are you sort of actively looking at, say like smaller gauge steel for lower temperature, kind of lower pressure systems going forward?
Yeah, so on your first question, really good question actually, is common issues in new markets, I guess, is and certainly being from the UK market initially, and working in DH for a few years now, it's very much a new industry which has grown slowly in the UK over the last 10 years. So there are experienced installers in the market, but when you're introducing new installers, that is where you have potential issues, because at the end of the day, it is down to the installer. So we've got fantastic products which take a lot of the human error out of it, but if you don't do your cleaning and abrading the casing properly, that's where you're going to get problems, and that is all down to the human interaction, obviously. We train all our installers on a minimum of a 3-day course or a 5-day, depending on how many different systems they want to go on. We train them in design, supervision. So lots of training goes on. So I would say get yourself an installer who's experienced. As they bring new installers in, new gangs, they'll be being supervised by experienced people. So I would say your danger is to bring in new installers with very little experience, because you are going to, they'll learn on the job, they'll make mistakes on the job, but you don't really want them learning on your projects. So we've got probably about a dozen approved installers, some of which are working obviously in Ireland at the moment on Grange Gorman and a couple of other projects. I don't know if that answers your question on that one. And then product development, always evolving products. In terms of the steel wall thickness, I'm not aware of going any lower. It's pretty thin wall steel as it is, because the pressures are relatively low. Temperatures are obviously coming down with later generation, 4th and 5th generation technology. But then you can go into plastic. There's a lot of talk of plastic at the moment, but you are limited by the size. So we go up to a maximum of 110. There are bigger ones out there, but they do then start to become, they don't compete on price with steel. So Scandinavia for however many years now, 40, 50 years, steel is the predominant product. House connections, by all means do it in a smaller diameter. But the big one really, I think, is one that I touched on and didn't really discuss in any detail whatsoever, is the leak detection. So with plastic pipes, you haven't got leak detection. So you can't be guaranteeing that you haven't got a leak in your system until you're starting to see big heat losses. You're starting to see the ground bubbling up with water, etc. So that is the big change, really. We are obviously looking at new products all the time, and we're constantly evolving. The diffusion barrier is a really important product for us in terms of getting those heat losses down. But I don't see any significant changes in terms of steel, etc. I think that's governed by the European norms. And it's not just on temperatures and pressures, really. There's several other factors to take into consideration there.
Thanks for that, Paul. We've got another couple of questions coming for you as well, Paul, related to the embodied energy or carbon of the piping. So have Luxor looked at this? That's the question from John Smith.
Yeah, thanks for that one, John. We have, we measure our embodied carbon. We're working, it's basically, at the moment, it's based on energy consumption in the production sites that we measure. So we're not looking at transport and our other suppliers, but where we're directly in manufacture, we look at the energy consumption, and we've got data on all of the plants. So I can share that with you if you like. If you drop me an email afterwards, I'll be quite happy to share that with you. But at the moment, it's limited to our own scope. It doesn't take in transport, etc. But yeah, we do.
That's great. And we'll share Paul's email is there on the screen as well, but we can circulate the presenters' details afterwards also. Another kind of follow-up question from John as well is there an environmental life cycle concern with district heating versus I presume district heating and decentralized systems? Has there been an analysis on this?
Not that I'm aware of. There may be somebody else on the call that has, but I'm not aware of it. Having said that, we are designing for a minimum 30, now 50 years. So we are looking at minimum 30, up to 40, 50, 60, up to 70 years as well now. So you are getting a long lifetime out of it. Yeah. As long as it's properly maintained and monitored. That's the key, really. And then, you know, at the end of the day, you have got the steel there. Okay, the PE casing, we are doing a recycled casing at the moment, made out of old fishing nets. So potentially we could recycle the PE, and obviously the steel can be recycled. So most of the materials that go into it could be reused in the future. So it's got relatively low carbon footprint, if you like, as a total whole life cycle.
Great. And just to add to that, then we did on one of the schemes in Dublin. On the Talis scheme, we had a student do his master's thesis, and a scientific paper as well was published on an environmental life cycle assessment of the Talis scheme there as well. So, and that turned out that the embodied carbon of the district heating scheme was a lot lower than the individual solutions for those buildings. And again, I can try and share a link, find the link to that report, and share that as well.
Yeah, that'd be great. Yeah.
And then I think there's one last question for you here, Paul. So Paul, another question from Paul Manning to Paul Atkinson. Would there be a rule of thumb on the rate of deterioration on installation re lambda if the diffusion barriers are not fitted as standard?
Yes, there is. But I couldn't tell you what it is. It depends on the diameter, basically. So the smaller the pipe, obviously the less insulation you have. So if you've got a 600 diameter steel carrier pipe, you maybe have 150 or 120 of actual PUR insulation. So it's only the outer layers that start to diffuse, and you lose the values. Obviously, the smaller diameters, where the DN25, DN40, etc., you maybe only have 20, 30, 40, 50 mil of insulation. So that will very quickly diffuse. I couldn't give you a rule of thumb because it is different depending on the diameter. What I can send over, though, are some graphs, if you like, of various different diameters and diffusion rates. That would help.
That's great, Paul. Another thing to add to our list for circulation after the webinar today. But great to see so many questions coming in for the speakers. It's a good bit of interest from the audience. That's great. So we have a question here open to all the panel. I think Matteo has put his hand up for this one. So advice to a building engineer as to what they can be doing or including in building designs now for district heating. So Matteo, if you want to jump in on this one.
I think the key point is not to make not to do choices that prevent district heating to be applied. That means, and this is a very important issue for Italy, having central heating versus diffuse heating in each single apartment. Any choice that puts single boilers at the apartment level will basically create a big barrier to district heating, while having a central heating is something viable that could, at some point, at a later stage, eventually be suitable for district heating. To be honest, for new settlements, taking into account the possibility to start from district heating is the best option, and that has lots of opens good opportunities for people living in the building, starting from safety down to all the advantages of district heating itself. Of course, this assumes that there is a district heating available, which may not always be the case. I would say that the most important thing is having central heating. Second level, of course, would be to rely on floor heating, or something that does not require very high temperatures, because that allows a better, wider adoption of low temperatures, which normally are possible in the future for district heating that are vastly based on waste heat. So in general, floor heating is better than radiators, just to it bluntly. But what I see in Italy, the key point is not relying to individual heating, because that really destroys the case for district heating, even at a later stage.
Yeah, so trying to go back and retrofit, obviously, when you've got a centralized system, is much more easily retrofit to a district heating system than individual solutions.
Absolutely.
And what we found, I suppose, as well, and some of from the Irish experiences is as well, is to make sure that the buildings are designed as well to ensure kind of a lower return temperature back to those centralized systems, and to ensure if a district heating system does connect, that you can provide lower return temperatures back into the network, which is beneficial, more efficient for the system. So is there any other questions here? I don't think so. If there's any last questions before we wrap up.
I think there was a point before from Fergus asking, I mean, making the point of small systems versus citywide schemes. I will give a very pragmatic answer based on the experience with the utility companies that we've worked with. Of course, when there is the political will and the capacity to work on a vastly planned scheme, that's better, because you can really plan in advance and try to achieve from the start a very efficient system. That is the case, for instance, of Ferrara, where there was a very, very interesting geothermal source and the waste heat source from industrial plants. And in that case, one of the maps you saw in my presentation covered, I mean, a large chunk of the population with really good involvement of the local authorities, etc. It is true, though, that these schemes require lots of commitment, and in many cases also require very, very large investments that are not always feasible. So what I see is that in many other cases, starting with smaller nets that then gets interconnected at a later stage is something that is happening in many, many cases. So I think that there is not one way of going through this. In a way, having something suitable that is sustainable and introduces district heating will eventually be leveraged upon at a later stage, while that gets interconnected, for instance, as different areas starts to be covered by district heating. The case of Milan that I mentioned before is I mean, there were two different areas. Milan is really huge, so it's could be considered a complex system, but the real reason to interconnect the two systems was that at some point when a waste-to-energy facility proved to be sufficient to cover part of the needs of the other network, the interconnection took place, and that actually led to a very interesting scenario in terms of energy mix and the decarbonization. So I think that smaller projects can be good, especially if they can be seen as the building bricks of future interconnected systems that may require too complex decisions to be taken at once.
Yeah, that's a good point, Matteo, and I've spoken from experience with other schemes in Europe as well, so that's good to hear.
Sorry, Dana, just on the previous question in terms of advice for building engineers, just aside from the whole kind of space for heat exchangers and the heating system itself, I think a simple thing that makes it a lot easier is having plant rooms adjacent to external walls, and on ground floors, and kind of having access just to kind of reduce those pipe runs, and also kind of outside the building, kind of safeguarding areas for pipe runs to run up to the building as well.
That's a very good point, John. Again, spoken from experience, working on the schemes in Dublin and working with developers and building engineers there. That's great. Thanks for that, John. So just to, I suppose, let people know that, as I said, this is the first in a series of training courses that we're planning in Ardea. So the next one is on the 30th of September, and we'll circulate more details on that course later on. Just say a big thank you to our technical support and our communications and the team behind all this. So a big thanks to Suzanne Fitzpatrick and Xavier Julisson for arranging the webinar, putting together the agenda for today and arranging the speakers and all that. So I think it was really good to see so many participants and a lot of questions coming in. So it shows that this is a popular topic, which is great. We just let people know as well, the Ardea conference is still planned, and fingers crossed we'll be able to shake hands at that event when that comes around in the end of November, so 24th of November this year. So we had arranged it for earlier this year, but obviously everything has been pushed back now. But that's still planned, that's still go ahead, and that's the venue is the Radisson Blue Royal Hotel in Dublin. So the Eventbrite page, I think, is Suzanne, you could jump in here, just let me know. I think the Eventbrite page is live and you can buy tickets at the moment, am I right?
Yeah, it's still live, and the early bird rate is going till the end of this month, I think. Yeah, so we have it open there on Eventbrite.
Great stuff. So even though it's the 24th of November, I suppose we want to make sure that you have it in your diaries now, because it is, I suppose, one of the very few district heating events in Ireland, and looking at the district heating sector. And it will be a very popular event. It was sold out at the last our last conference last year. So do get your tickets early for that. If there's any specific questions you have, or any information you would like on joining Ardea and becoming a member, we would love to hear from you. Our email address is info@districtenergy.ie. So do get in contact with us if you do want to join, and more information about membership and about Ardea in general on our website that David showed earlier, including the heat atlas, and that is also on this districtenergy.ie. You can also check out our Twitter if you want to keep up to date on any of our training sessions and conferences and any updates there. It's at Ireland DEA is the Twitter handle. So just a big thank you then, I suppose. If there's no more questions, a big thank you to our speakers for taking the time to be here and putting the presentations together. I think it was good to get an overview right from a very high level that David started off with, right down to the very specifics of district heating design. Great to see as well. I had to give a shout out to the two female participants online as well, to Sarah and Shirley. Thanks for joining us. Good to see some other women involved in the district heating area. So I have to try and promote a bit of diversity while I'm on here. We'll, as I said, we'll keep in touch, and we'll email everybody afterwards with all the follow-up bits and pieces and links that we promised during the webinar. And so thank you very much, and we'll hopefully be able to join us again at the next webinar. Thank you.
Thank you very much.
Cheers, Donna. Thank you.